Most of the physics that you learned in a high school physics class is really old. For the most part, we have worked with Newtonian physics, which stayed mostly the same since the 17th century, but that doesn't mean there's nothing new happening in physics. Physicists are working on exciting applications of these old laws and principles, sure, but they're also working in fields that are slightly newer. This week, we're talking specifically about these newer branches of physics that are much stranger than you might expect. In your first assignment, you learned about special relativity, which was introduced by everyone's second favorite physicist, Albert Einstein, in 1905. Okay, so that isn't exactly yesterday, but it isn't the 17th century either.
The special theory of relativity, as you should know from assignment 1, centered on the ideas that the laws of physics are the same in any inertial frame and that the speed of light is the same for all observers. This happens because of your relativistic movement's implications for time dilation. Although you only experienced 4 years, your relative speeds meant that your sister would have observed that time passing tenfold. As you can now play the younger version, at least you can now play the younger version of your sister in the upcoming biopic about her life, though. We can also use really cool graphical methods to show how special relativity affects things like sequences of events using something called a Minkowski diagram, which I won't get into here, but I might include as a fun solved problem on Classroom after I finish this video. While special relativity is crazy and mind-bending, Einstein got even weirder in 1913 when he pushed out his second model of relativity, general relativity. Now, general relativity is much more complex mathematically than special relativity, so we won't touch on the math, but the implications are really cool. To begin, both of Einstein's relativity models are based on the idea that instead of viewing space and time as two separate entities, we should view them as one combined entity called space-time. Special relativity tells us that even though we are usually locked in and move through the time dimension at a fixed rate over which we have no control, that doesn't need to be the case. While we couldn't go backwards in time, we could absolutely change the rate at which we move forwards in time by changing our speed. General relativity takes this a step further by saying that space-time makes up a grid that can be warped by massive bodies. Think of a trampoline. If I place a bowling ball on the trampoline, the material will stretch and warp to create a curve leading to the bowling ball. I can do the same thing with a basketball. The bowling ball being larger than the basketball would produce a larger curve. Similarly, more massive objects will cause larger curves in space-time around them. These curves in space-time manifest in a few ways. First, they make us experience a stronger gravitational pull closer to a more massive object. Second, because of his famous E=mc² equation, Einstein says that mass and energy are equivalent and can be related through the square of the speed of light. This means that things with a lot of energy act as sources of gravity too.
Third, the frequency of light waves is affected by the curves in spacetime, causing observed light to be bluer, closer to a massive object, and redder further away.
This leads to the fourth, and potentially coolest result. Time itself moves more slowly closer to a massive body than it does farther away. While both special and general relativity may seem far-fetched, there have been multiple experiments that have corroborated their explanations. Things like gravitational lensing, where light bends to follow the curves in spacetime around massive objects, gravitational redshift, where the light from massive objects is shifted toward the red end of the spectrum, and gravitational time dilation, observed by transporting atomic clocks to vastly different altitudes, corroborate general relativity, while tests including the Ives-Stilwell, Kennedy-Thorndike, and Michaels-Morley experiments, which looked at the Doppler effect in light, the presence of length contraction and time dilation, and the constancy of the speed of light, respectively, and the flying of atomic clocks at high speeds have corroborated special relativity.
While Einstein's work is important, it's not the be-all and end-all of modern physics. To find out more, you'll want to check out the extra assignments on quantum mechanics and string theory. Quantum mechanics deals with objects on the subatomic scale, and centers mainly on how movements and positions on such small scales are ruled by probability, and much is left to chance. This is at odds with the neatly structured world of the general relativity, which is a problem that string theory seeks to solve. In fact, there's a fun little vignette that's told about Einstein and another physicist of the time who worked on quantum mechanics, Niels Bohr. So Einstein is quoted as having said to Niels Bohr that God doesn't play dice with the universe, meaning that
quantum mechanics couldn't possibly be true because of the way that it doesn't have neat and predictable rules. Niels Bohr reportedly responded by saying to Einstein, "Don't tell God what to do with his dice."